In this section of the book, we look at the most simple kind of differential equation. In fact, they're so simple, most people don't think about them most times as differential equations. They just think of them as undoing differentiation, so anti-differentiation, anti-derivatives. So we want to solve for y dy dx equals some given function of x. So this means you need to find some function. You're given little f of x. You're trying to find some function y whose derivative is the given function. So you're anti-differentiating. You're figuring out a function whose derivative is little f of x. So an example. Solve dy dx equals 3x squared. Well, how do you do this? Hopefully, you can quickly think of a function whose derivative is 3x squared, namely x cubed. One solution is y equals x cubed. Because if y is x cubed, its derivative is certainly 3x squared. Are there others? Sure. There's another one. Another one. Y equals x cubed plus 7. Right? Because when you differentiate x cubed plus 7, the derivative of x cubed is 3x squared, and the derivative of 7 is 0. So yes, here's another function whose derivative is 3x squared. But it's kind of, all I did was add a constant. Is every solution, what we'd like to know is what the general solution is. Is every solution to y equals 3x squared, is every solution something of the form x cubed plus a constant? And the answer is yes. On any interval on which the differential equation was supposed to be satisfied, because we have a theorem that we went over, the mean value theorem. Actually, one of the consequences of the mean value theorem was that if two functions defined on an interval have the same derivative on that interval, then they differ by a constant. In other words, if you know one of the functions, then the other function has to be the given one plus some constant. So how do you find antiderivatives? Like all the antiderivatives, so all the solutions to dy dx equals a function of x, you find one of them, and then you put a big plus c or plus something else that could be a constant. So the general solution to this differential equation, the set of all the functions, makes this true. We write the solution like this, where c could be any constant. Okay. What this means is that all of our differentiation rules give us anti-differentiation rules. So this y, yeah, I should write that somewhere. This is the general antiderivative of 3x squared. It's a set of functions, a whole collection of functions. You pick different constants, you get different antiderivatives, but we write all of them like this. The notation for this is that you write this. So what is this? You read this as, and this is another term for the antiderivative, the integral of f of x with respect to x. So, or some people would say the indefinite integral. So antiderivative, a lot of people call this just the indefinite integral, and if it's clear from context, they just say integral. In an integral calculus course, there is something called the definite integral. It's a kind of continuous sum of infinitesimal contributions. And it's closely related to taking antiderivatives. There's the fundamental theorem of calculus, which tells you how finding antiderivatives relates to calculating definite integrals, this continuous sum of infinitesimal contributions. But for right now, we'll refer to antiderivatives sometimes as integrals or indefinite integrals. And so you read this as the integral of f of x with respect to x. So this is a combination symbol. This together with this. This and this tell you to anti-differentiate whatever is right here with respect to that variable. So it's kind of the inverse operator to d dx, which says differentiate a function with respect to x. It says anti-differentiate whatever is written in between with respect to x. So this is anti-differentiate. So what you would write here is that the general, it means the general antiderivative, so including this arbitrary constant that could be anything, the antiderivative of 3x squared with respect to x, you'd write it's x cubed plus c, where c can just be any constant. All right? This means that all of our differentiation rules give us anti-differentiation rules. You just kind of read backwards and add a plus c. So for instance, the power rule, I'm going to include some parts that are special cases of the power rule. Some people wouldn't lump these into what they call the power rule for integrals. So the power rule for integration or anti-differentiation so, well, one of them, what is the antiderivative of 0? Something whose derivative is 0. Well, 0's derivative is 0, but then you can add any constant. And what this is the same as saying is the derivative of any constant is 0. You can always read anti-differentiation formulas backwards. Saying that the antiderivative of this with respect to x is this means exactly that the derivative of this with respect to x is whatever's written in between this thing that's called an integral sign and the dx. The integral of 1 dx. Something whose derivative with respect to x is 1. Oh, well, that would be x plus some arbitrary constant. The big case, 3, is if p is unequal to minus 1, the antiderivative of x to the p with respect to x, you add 1 to the exponent, divide by the new exponent, and put in a plus c. Why is this? Because you take the derivative of this and you make sure you get x to the p. The derivative of this by the power rule. So here p is a constant. I don't know if that was clear, but I meant p is a constant. If you look at the derivative of x to the p plus 1 over p plus 1, the 1 over p plus 1 is a constant. And then the derivative of x to the p plus 1 by the power rule for differentiation. You bring the exponent down as multiplication, and you subtract 1 from the exponent. But then the p plus 1s cancel, and you get x to the p. You can't do this if p is minus 1. There should be a big, the formula itself should tell you that. If p is minus 1, you'd be dividing by 0. That's a big no-no in math. So yeah, you can't do this if p is minus 1. If you want to lose a lot of credit on a test, just go ahead and say that antiderivative of x to the minus 1 is x to the 0 over 0, which is undefined. That's really bad. What is does that mean there is no antiderivative of x to the minus 1, or what's the same thing? 1 over x dx. No. You know a function whose derivative is 1 over x. Natural log of x has derivative 1 over x. In fact, natural log the absolute value of x is the most general antiderivative up to the plus c, because that works when x is positive or negative. So this, you get the natural log of the absolute value of x plus a constant. So this tells you how to differentiate powers of x. This is like this is special with a 0 here. But here this is like x to the 0, except you'd have to worry, if I wrote x to the 0, you'd have to worry about, oh, what about when x is 0? For all the x's unequal to minus 1, you get this kind of reverse of the normal power rule for differentiation, and then something special happens when x is minus 1. All right, so what's an example of using this? Well, you could phrase it as an initial value problem. So a differential equation with an initial condition. So example, solve dpdr equals the square root of r. So the derivative of p with respect to r is the square root of r. And when r is 9, p is minus 7. Solve this initial value problem. So a differential equation with some initial data. Well, this says p is something whose derivative is the square root of r. So p is an antiderivative of the square root of r with respect to r. Write this as r to the 1/2. So an antiderivative of r to the, or the general antiderivative of r to the 1/2 with respect to r, you add 1 to the exponent, so you get r to the 3/2, and you divide by the new exponent, 3/2, and you put in a plus c. We can invert and multiply this, so you get p is 2/3 r to the 3/2 plus c. This is the general solution to the differential equation, but we have some data that when r is 9, p is minus 7, so we can solve for this c. So p is minus 7 when r is 9. So we get the r 9 to the 1/2 is the square root of 9, that's 3. So this is 3 cubed, that's 27. So we get minus 7 equals 2/3 of 27 plus c. This is 18, right? 3 goes in 27. 9 times 18. So we get minus 7 equals 18 plus c. So c is minus 25. So you take that constant and you put it in there, and our solution to this initial value problem is p equals 2/3 r to the 3/2 minus 27. And that's the solution to that initial value problem. All right. What other rules do we get? Well, I'm not going to list all of our rules in reverse, as all our rules for differentiation in reverse to give us anti-differentiation formulas, but I'll list a lot of them. A very important one is linearity. Since differentiating is linear, if you take the derivative of a sum of constants times functions, then you just take the derivative of each function, multiply by the constants, and then add. Anti-differentiation works the same way. If you want an antiderivative of a constant times a function plus a constant times another function, what do you get? You can split up the sum, you can pull out the constants, and you get a times f of x dx plus b times the integral of g of x dx. What does this mean? It means, so what happens with the plus c's? It can be, there might be a slight worry there. In fact, if a and b are 0, this isn't quite true. Because if a is 0 and b is 0, then over here you get 0. And over here, well, even if a and b are 0, you're anti-differentiating 0 and you get a plus c. So really, either you have to make the special exception that a and b can't both be 0, or you have to explicitly add a plus c over here. So, but aside from that, this, oh, maybe all right. It's, a and b are not both 0. So, how do you use this? Well, let's anti-differentiate something like 5x cubed minus 7 times the square root of x. So what do? You split up the sums and differences. So this could have been a plus or minus because b could be a positive or negative number. You split up the sums or differences, you pull out the constants, and you get that this should be the same as 5 times the general antiderivative of x cubed minus 7 times an antiderivative of the square root of x, that's the same as x to the 1/2. If you write it like this, you get this is 5 times an antiderivative of x cubed, the power rule for integration. You add 1 to the exponent, you divide by the new exponent. Now, we should get a plus c here, but we'll get another one over here. So I'll call this one c1. And it's technically multiplied by the 5. And then you get minus 7 times. Then you do the power rule for integration again. You add 1 to the exponent and divide by the new exponent. And you could get a plus c2 here for this indefinite integral. So this answer is correct. But most people don't bother writing it this way because if you multiply the 5 times c1 and the minus 7 times c2, and times the other parts that you're supposed to, you get 5x to the 4th over 4. I'm going to write the constants last. You get minus, if you invert this and multiply, you get a minus 14 thirds x to the 3/2. And then for the constant, you get plus a 5c1 minus a 7c2. But c1 and c2 could be anything, any real numbers. They're just some constants. And so 5c1 is just some other constant. It could be anything. And minus 7 times c2 could just be any constant. And their difference, or their sum, 5c1 minus 7c2, is just some number that could be anything. And so the standard practice is just to lump those together and write one big plus c. And it was supposed to equal this original indefinite integral, which would have plus a constant times it. So yes, the rule says this, and I had to write a and b are not both 0 so that the plus c's don't get completely wiped out. But in general, what happens? When you've got a sum or difference of a bunch of indefinite integrals multiplied times constants, you just produce one antiderivative for each integral. So you don't bother putting in the plus c's. You just go, oh, x to the 4th over 4 and x to the 3/2 over 3/2. And then you write all of those. And then at the end, you put one big plus c because all the rest of them can be lumped together, can be grouped together and just called a constant. Okay, we can already do a very serious physics problem. So why don't we? In physics class, they almost always take the example of something is moving with constant acceleration, like maybe the acceleration due to gravity, but is moving with constant acceleration, and you're asked to find the velocity and the position. So suppose an object is moving with constant acceleration a. Find the velocity v as a function of time and the position p as a function of time. Okay, well, I haven't given any units, but assuming we pick consistent distance and time units, this will be, you could use this for whatever units you have, meters and seconds, feet and seconds, miles an hour. So what do we know? We know that velocity is the derivative of the position with respect to time. And acceleration is the derivative of velocity with respect to time. These are exactly the same things as saying, oh, that v is an antiderivative of the acceleration with respect to time, and the position is an antiderivative of the velocity with respect to time. Those say exactly the same thing. Saying that v is an antiderivative of a means the derivative of v with respect to t, this variable, is that, yes. And writing this antiderivative equation means exactly that the derivative of the position with respect to time is the velocity. Yes. This is true regardless of what the acceleration is. But if the acceleration is constant, then that a is a constant. And what's the antiderivative of a constant? Well, you can pull that constant out by linearity and just get that it equals a times the integral of 1 dt. You can do that because a is a constant. If a is not a constant, that's simply not true. But the integral of 1 with respect to t is just t, and so we get at plus a constant. So we find that if the acceleration is constant, then the velocity is that constant acceleration times t plus a constant. Now, in that formula, mathematically, we just get that c is any constant. Of course, physically, we'd like to know that that constant has some meaning for us. So what we've just found is that the velocity equals the constant acceleration times t plus some constant. Can we give that constant some physical meaning, even though we're given no other data in the problem? Well, we plug in what I refer to as tautological initial data. Plug in that v at time 0 equals v sub 0. What? What am I writing? I'm saying we're not told what the velocity is at time 0, but just call the velocity at time 0 v sub 0, v naught. So then this equation says the velocity at time 0 equals the velocity at time 0. It shouldn't say anything. Or what it says is so obvious. Well, that's why I call it tautological. A tautology is something that's true just from logical reasoning. So that's clearly true. And then, strangely, kind of, if you plug that into here, you get physical meaning for c. You plug in that when t is 0, v is v naught, and you get v naught equals a times 0 plus c. But this is 0, so that means c equals v naught. And then, so then you take these two equations and you combine them, and you get v equals at plus v naught. No one has to give you any extra data for you to conclude that this c is the initial velocity. It just follows from the equation itself. It's really cool in that respect. So, okay, if the acceleration is constant, we get that the velocity is the acceleration times time plus the initial velocity. What about the position? Well, the position, p, is an antiderivative of the velocity with respect to time. But we now know the velocity is at plus v naught. and you anti-differentiate with respect to t. That's a constant, that's a constant. There's a sum. By linearity, we can split up the sum and pull out the constants. We get that this is a times t dt, or the integral, a times the integral of t dt, plus v naught times the integral of 1 dt. This is a times, this is the power rule. This is t to the 1. So you add 1 to the exponent, divide by the new exponent. So you get a times t squared over 2 plus v naught times the integral of 1 dt is just t. And then you get plus another constant. And this is the position function. This c is not the same as the plus c I had before. Since we already figured that one out, I'm reusing the big plus c. This happens all the time in calculus class when you start anti-differentiating. So again, we would like to give some physical meaning to this currently arbitrary constant. So we get the position is 1/2 at squared plus v naught t plus a constant, but we'd like to give this constant some physical meaning. So once again, we plug in tautological initial data. P at time 0 is p0, p naught. It says the position at time 0 equals the position at time 0. That's certainly true. But if you plug that in here, then when t is 0, p is p naught. You get p naught equals 1/2 a times 0 squared plus v naught times 0 plus c. Well, this is 0, so you just get c as p naught. And then you plug that back in up here, and it gives physical meaning to this seemingly arbitrary constant. You get 1/2 at squared plus v naught t plus p naught. And that's our solution for the position as a function of time. That relied heavily on the fact that we were assuming the acceleration was constant. But with our differentiation formulas, being able to be read backwards to give us anti-differentiation formulas, we don't need for the acceleration to be constant to figure out the position as a function of time. We'll get different formulas if the acceleration is not constant, but we can handle lots of non-constant acceleration problems. So let me first give you another couple of anti-differentiation formulas. Like antiderivative of cosine of x. Something whose derivative is cosine. Sine. The derivative of sine is cosine. And then you put in a plus c. And then, well, what's an antiderivative of sine? Something whose derivative is sine. That's not so easy. The derivative of cosine is negative sine. So if you think for a minute, you'll get that this is negative cosine plus c, because being an antiderivative means if you differentiate this side, you get what's in between the integral sign and the dx. The derivative of cosine is negative sine. So the derivative of negative cosine is negative sine. It's sine. So this is what you get. This actually leads to quite a bit of confusion because these formulas look backwards in some sense from the derivative formulas. The derivative of sine is cosine, but the antiderivative of cosine, but the antiderivative of sine is negative cosine. The derivative of cosine is negative sine, but the antiderivative of cosine is plus sine. So it looks like the negatives have switched when you do antiderivatives. This shouldn't cause you any confusion. You should always think of it in terms of derivatives. The derivative of this should be this, and the derivative of sine is cosine. The derivative of this should be this. It's the derivative of negative cosine equals sine. All right, so let's do an acceleration problem now where the acceleration of an object, suppose the acceleration is not constant. but that the acceleration is the sine of t, where t is the time. How does that change what we got before? You might think, I just take this formula that I had for constant acceleration, and where I had an a, I replace the a by the sine of t. No, that's completely wrong. You don't do that. You have to do the antiderivatives. So you find that the velocity is the antiderivative of the acceleration with respect to time. That's always true by definition of acceleration and velocity. But now you put in that a is the sine of t. Oh, but the antiderivative of sine of t is minus the cosine of t plus a constant. We'd like to give physical meaning to this plus c, and after this example, you may think, oh, well, it's the initial velocity, just like it was in the last problem. No, it's not. And you have to actually do the work to see that it's not. So we've got the velocity is minus the cosine of t plus a constant. Yes, we plug in the tautological initial data, that at time 0, the velocity is the initial velocity. And then, so we get the initial velocity equals minus the cosine of 0 plus this constant c. But the cosine of 0 isn't 0, it's 1. So this is v naught equals minus 1 plus c. So this c is actually v naught plus 1. And now you take this and you plug it in up there, and what we get is that we find that the velocity is minus the cosine of t plus v naught plus 1. Okay? So that's the velocity. What's the position? The position as a function of time is always the antiderivative of the velocity with respect to time. This is now minus the cosine of t plus v naught plus 1 integrated with respect to t. This is a constant. V naught's a constant, v naught plus 1 is a constant. So we can split this up and pull out the constants, and we pull out the minus 1 for that matter. We get minus the antiderivative of cosine of t plus of v naught plus 1 times the integral of 1 dt. And you get antiderivative of cosine, sine. So you get minus the sine of t plus of v naught plus 1 times t plus a constant. This. So we're just about finished. We need to figure out this plus c in terms of the initial position, and we'll be happy. So we just derived that the position is minus the sine of t plus v naught plus 1 times t plus a constant, and then you put in that at time 0, the position is p naught, the position at time 0. And you get p0 equals, at time 0, this is 0, this is 0, and you get plus c. So this c is the initial piece of data. It is the p naught, the initial value of the function. So we get p equals minus the sine of t plus v naught plus 1 times t plus p naught. And this is our solution for the position. This part looks sort of like what we got in the constant acceleration part, except for this bizarre plus 1. This part doesn't look anything like 1/2 at squared. Oh well. There are a couple of other of our differentiation formulas that I'll go ahead and state in reverse as anti-differentiation formulas because they come up fairly often. And then I want to look at the chain rule as an anti-differentiation formula, and the product rule is an anti-differentiation formula. Kind of strangely, the product rule is kind of the hardest one. Actually, that's not fair. The quotient rule is so hard as an anti-differentiation formula, we don't even use it as one. So I guess it's not fair to say that the product rule is the toughest. So, but let's look at what is an antiderivative, or the general antiderivative of 1 over 1 minus x squared with respect to x. We need to think of something whose derivative is this. Well, we know something whose derivative is that. It's inverse sine plus a constant. And then what's an antiderivative of 1 over 1 plus x squared dx? We need to think of something whose derivative is 1 over 1 plus x squared. That's the inverse tangent of x plus a constant. And those indefinite integrals come up all the time. So you should just know them. All right. But now I want to look at the chain rule and the product rule in reverse. So the chain rule is an anti-differentiation formula. The chain rule says the derivative, I'll remind you what it says. It tells you that the derivative of the composition of functions, so you do the function f to g, and you get the derivative. You take the derivative of the outside function, you leave the inside stuff how it was, but then you have to multiply it times the derivative of the inside function. As an anti-differentiation formula, this says that an antiderivative of this is f of g of x. So it says an antiderivative, or the general antiderivative of f prime of g of x times g prime of x dx equals f of g of x plus c. Okay, that's true. It's the chain rule in reverse. No problem. What's slightly nicer is if you, or actually substantially nicer, is if you look at it in a slightly different form. It's kind of like Leibniz's form for derivatives, except now for antiderivatives. So we just said, oh yeah, the chain rule. It says this. In reverse. So it's an anti-differentiation formula. That's true, but it looks a lot nicer if you let u equal g of x. So you have an integral. You see that some function is done to some other function, and then there's other stuff in the problem like this. So you let u be g of x, and then what happens? Then this integral is f prime of, well, u. G prime of x is du dx, and you integrate that with respect to x. And what this says is you end up with f of u plus a constant. Then you would put back in that u is g of x, and you get this answer. But this is the same, f of u plus a constant is the same as the general antiderivative of f prime of u with respect to u. Right? Because the derivative of this with respect to u is just f prime of u. So an antiderivative of this with respect to u is f of u. But the fact that this equals this means exactly that it looks like the dx's are canceling. Now, this is not a fraction. And this is just part of an instruction telling you what to anti-differentiate with respect to. But this is so helpful that it looks like those cancel, that's how we talk about it, and that's how we think about it, and that's how we make sure we get it right. It also means that our differential notation that we used for differential approximation is very useful. It means if we continue with our notation that this part equals du, right? If these were canceling, then you would get this quantity du. That's not what's happening, but we use that notation in the sectional and linear approximation and differential approximation. And it's extremely helpful when doing the chain rule in reverse, that you write, oh, I'll let du be du dx times dx, And then this part of what we're doing just looks like it's algebra, when in fact, it's the chain rule. Okay, when you do this, this is usually referred to the chain rule in reverse, where you name part of it u and use that du is du dx times dx. This all goes by the name substitution, or integration by substitution. So integration by substitution. And the favorite variable name for substitution is u, but of course you don't have to use u. About the only variable name that would be bad here would be x or f or g. But so let's do a couple of examples of using substitution. So I've got a couple of particular ones I'd like to do. So, an example of integration by substitution. We'll do two of them kind of side by side. The cosine of e to the x plus 7, and then that's times e to the x dx. And then another one, the integral, the antiderivative of t over 1 plus t squared dt. All right, let's look at both of these. So suppose we weren't talking about substitution. You just needed this antiderivative for a problem. You're told either calculate this antiderivative or solve this differential equation, and it boils down to this. How would you know to do substitution? Well, you look at this integrand. So yes, that thing in between that we're finding an antiderivative of is also called an integrand. You look at the integrand, the thing you're trying to antidifferentiate, and you should think, is that the derivative of some function I've got memorized? So have you memorized some function whose derivative is cosine of e to the x plus 7 times e to the x? No, I hope not. Okay, it's not a function you have memorized. The next thing you should hope that it is an easy substitution. And that means you should quickly kind of recognize something as being this inside function u. So the g of x, the inside function u, something that you've done another function to that appears in the integral. Well, in this problem, that's pretty clear. We've got cosine of e to the x plus 7. And so what you should hope is that the substitution, where you let u equal e to the x plus 7, would work, that it would change this integral into something easy. Let me give myself more room. I'll put this one back in a minute. But, so what do you write at this point? You write that du is du dx times dx. Du dx, the derivative of u with respect to x, is e to the x plus 0. So it's just e to the x times dx. Oh, well, that's exactly what's right here. We have an e to the x dx. So this integral becomes, this part's u, so you get the cosine of u, and the e to the x dx is exactly du. And so the chain rule in reverse, substitution says, you do this integral. You anti-differentiate this with respect to u. But the antiderivative of cosine of u with respect to u is sine of u plus a constant. And then you put back in what u was. U was e to the x plus 7 plus c. And this is what you get. Of course, it's just the chain rule in reverse, because if you differentiate this, you differentiate it by the chain rule. You differentiate the outside function. You get cosine of the inside stuff, but then by the chain rule, you have to multiply times the derivative of the inside stuff. So you get cosine of e to the x plus 7 times the derivative of e to the x plus 7. But that derivative is just e to the x. Yes, you get cosine of e to the x plus 7 times e to the x. Right. Okay, what about the other one that I had up there but erased? The integral of t over 1 plus t squared dt. How do you integrate that? Well, by substitution. But how do you see that? Well, it's not as easy to see this time because there's no clear function done, maybe done to the 1 plus t squared. So maybe it doesn't look so obviously like a substitution. You might also think, oh, isn't that inverse tangent or something? If this were a 1, this would exactly be the inverse tangent of t plus a constant. This is not a 1, it's a t. And you should think for a minute, do I know a function whose derivative is t over 1 plus t squared, or x over 1 plus x squared with respect to x? And you should know that you don't have one of those memorized. And then you should hope that this is a substitution. And if it is, then you should look for something kind of complicated that can be u, and so that essentially everything else in the integral is du, including the dt. Well, it doesn't take too long to see that if you let u be 1 plus t squared, then du is du dt times dt, which is du dt, the derivative of u with respect to t, 0 plus 2t. So you get a 2t times dt. Oh, well that's nice because this integral is the integral of 1 over 1 plus t squared. And then you can write this t, and it'd look slightly better if you wrote it next to the dt. So this is the integral of 1 over u. We have a t dt. Here's a t dt. We don't have this 2. But if you divide by 2, divide both sides by 2, you get a half du equals t dt. And then where you had the t dt, you replace it with times 1/2 du. But this is multiplying by a constant, and antidifferentiation is linear. We can pull out the constant 1/2, and then you get times the antiderivative of 1 over u with respect to u. But this one is one you have memorized. This is the natural log of the absolute value of u. And you need an arbitrary constant. And then you put back in that u is 1 plus t squared. And you get 1/2 the natural log of the absolute value of 1 plus t squared plus a constant. And that's our general antiderivative. Do you really need the absolute value signs? Well, in general, when you integrate 1 over u du, yeah, you should get the absolute value of u. Here, u is 1 plus t squared. That's always positive. So no, well, you don't need the absolute value signs here. They're not wrong, but you don't need them. The absolute value of 1 plus t squared is the same as just 1 plus t squared. So here you can write your answer like this. Okay, there's one other differentiation formula that I want to go over in reverse. It's fairly complicated. It's the product rule in reverse, which doesn't seem like it should be complicated. And yeah, it is. So the product rule in reverse just says that if you take this antiderivative and add this antiderivative, you should get f of x times g of x plus c. Why? Because the derivative of f of x times g of x is the first thing times the derivative of the second, so it's this part, plus the second thing times the derivative of the first. So yes, the derivative of this is the f g prime of x plus g of x f prime of x. This is the product rule in reverse. How this gets used as an anti-differentiation formula, though, is slightly different. So the standard letters that are used, you don't have to use these, but this is what everybody likes to do, is to let u be f of x and v equals g of x. That means that du is f prime of x dx, and dv is g prime of x dx. And so this formula becomes, this one that I've got written, f of x is u, g prime of x dx is dv, plus g of x is v, f prime of x dx is du, and then it equals f of x times g of x, that's u times v plus a constant. And then you put this part on the other side, and you get the integral of u dv equals u times v minus the integral of v du. And you don't need to bother writing the plus c, because now that there's an indefinite integral on this side, it already includes a plus c. Before we had two plus c's on the same side. But you get this. This is what most people memorize as integration by parts. It is the product rule in reverse. So for antiderivatives. How on earth do you use this? You see an integral, and you suspect that it came from the product rule. Sorry, let's try that again. You see an antiderivative, and you see that the integrand, the thing you're trying to anti-differentiate, looks like it results from the product rule. Although what that means, I mean, with enough experience, you can kind of tell when things are likely to have resulted from the product rule, but sometimes it's hard to tell. But what do? Then you name part of what you see in your integrand u, and the rest of it has to be dv. And then you figure out du and v, apply this formula, and hope that this new integral, the integral of v du, what you get when you switch the roles of u and v, is easier than the integral you started with, or at least no more complicated. All right, this will all become a lot more clear when we do some examples, so let me show you how this gets used. I'll do 4 of these because they do take some getting used to. I will not do a complicated one where after one integral you get an integral that's clearly exactly as hard as the one you started with, so it looks like you're not getting anywhere. I'll let you read that one, but if you integrate again twice and do something clever, if you integrate again by parts, do something clever, you do get the answer. But all right, so let's look at the integral of z, e to the z dz. Okay, how do you integrate this? Well, it takes some experience to decide how you should integrate it, because if you had e to the z squared, z e to the z squared dz, the substitution u equals z squared would be good, because if u is z squared, then du would be 2z dz, and you have a z dz left over. So yeah, you integrate this one by substitution. So you might think you'd do this one by substitution, like let u be z. That substitution never helps. Let u be z, the variable that's there, because then if u is z, then this integral just becomes the integral of u e to the u du. You have exactly the same integral, just with u's every place you had z's. So it takes some experience to recognize this will not be a nice integration by substitution. But you do see that it's the product of two very different looking kinds of function of z. Now, so was z e to the z squared. So some of it's a matter of experience. But you look at this, you don't see a substitution that will help, and then you agonize over the fact that, maybe I have to use integration by parts. All right. And it's reasonable because this does look like the product of two very different kinds of functions. So you think integration by parts. All right. The integral of u dv equals u times v minus the integral of v du. Here's your integral. You pick part of the integrand to be u. Everything else, including the dz, then would have to be dv to use this. And you go ahead and write what those are, and then you pick u that determines dv, you calculate v from dv, you calculate du from u, and you apply this formula and hope that this new integral is easier. I'm going to do this the good way, and then show you what happens if you try to do it the bad way. There's a choice of what part to pick for u of this integrand. You could, even after you're told it's an integration by parts, it would be reasonable to pick u to be z or u to be e to the z. One of those is a good choice, one of them is not. A lot of this, again, is experience, but let me do it the way that works well and then show you what happens if you make the bad choice. So we're going to let u be z, and we're going to integrate by parts. So we want to write this as the integral of u dv. So if u is z, then the rest of this, so if this is going to be u dv, and that part's u, then this part better be dv. Then dv needs to be the e to the z dz. So if u is z and dv is e to the z dz, then this integral is the integral of u dv. And integration by parts tells us that this is u times v minus the integral of v du. But to use it, okay, we need what v is and we need what du is. Right? If u is z, du is du dz times dz. Du dz, the derivative of u with respect to z is just 1, so we get 1 times dz. So du is just dz. Okay. What about v? Well, v is the antiderivative of dv, which is the antiderivative of 1 times dv. And that means that this is the antiderivative of e to the z dz, or the antiderivative of e to the z with respect to z. What's a function whose derivative with respect to z is e to the z? E to the z. And here's something that happens in integration by parts. When you calculate v as the integral of dv, you don't usually put the plus c. It isn't wrong to put it in there. And there are some rare occasions where it's helpful to put in the right constant. But we need some v that works. We don't need the most general v. So it's extremely unusual to put a plus c on your calculation of v in integration by parts. So we'll just use v equals e to the z. Okay, so what do we get? We picked u, it determined dv. Then we had to calculate du and had to calculate v. And the reason we picked those was so that we could apply integration by parts. So this integral became the integral of u dv with this choice, which determined this. Integration by parts says it equals this. What is u times v? It's z times e to the z. This is z times e to the z. That's u dv. That's u times v. Z times e to the z minus the integral of v, which is e to the z, du, which is dz. Oh, so we have to anti-differentiate e to the z with respect to z. That's e to the z. And so what we get for an answer is z e to the z minus e to the z plus a constant. And that's our answer, obtained by integration by parts. All right? What happens if you make the bad choice? What happens if you looked at this, you realized it should be integration by parts, but instead of picking u to be z, you pick u to be e to the z? You don't get something that's wrong, you just get something that's not helpful. Your integral becomes harder than it started out, which is not good. So suppose you have this. You realize it's integration by parts. So you realize that part of this should be u. The rest of it will be dv. But instead of letting u be z, you let u be okay, you can do that. That means that the rest of what you see in the integral, the z times dz, that would be dv. Then the dv equals z dz. Fine. So then this would be the integral of u dv, no problem. By the integration by parts formula, which is just the product rule in reverse, this is u times v minus the integral of v du. All right, if u is e to the z du, is its derivative times dz. So we get this. That's not bad. V is the antiderivative of dv, but we don't care about the plus c. So it's the antiderivative of z dz. This is the power rule. This is z to the 1. So the power rule for integration. You add 1 to the exponent and divide by the new exponent. And don't bother putting in the plus c. So what do you get after you apply integration by parts? U times v, e to the z times z squared over 2. Minus the integral of v, which is this, z squared over 2 times du. du is e to the z dz. So we get this. And it's your hope that you start with this integral and you apply integration by parts. So you make a choice for u, it determines dv, you apply integration by parts. It's your hope that this new integral is easier than the one you started with, or no worse. But it clearly got worse. The e to the z is as bad as it was, and the power of z went up. This is not good. You could try integrating this by parts again, and only one of two things would happen. So you might pick, well, I guess you could make a third bizarre choice, but you could either let u be the z squared over 2 part, which would mean dv is e to the z dz, or you could let u be e to the z and dv be z squared over 2 dz. And the third choice, which would be a little weird, is like let u be z, take one of the z's, let u be z, and that would make dv z over 2 times e to the z dz. Anyway, what happens if you make those choices is either you end up back where you started, over here, or your power of z goes up again, and you get a z cubed. So this is a bad way to go, and you should recognize this quickly after, if you were to make this choice. Part of what happens is frequently, not always, and I'll do an example in a minute where it's not true, frequently, if you've got a power of your variable times some other function and its integration by parts, you want the power of the variable to be u, so that when you take du, the power drops by the power rule for differentiation, so that you end up with an integral with a smaller power in it, instead of, if you integrate, having the power go up, which is what's causing the problem here. Okay, let me change this problem. Let's suppose that we started with the integral of z squared e to the z dz. So that's effectively where we ended up by making the wrong choice in the other integral. But let's suppose you had started with this integral as your problem. Then what would you do? Well, if you believe what I just said about picking the power of z to be u, and you think this is an example where it works, then you should let u be z squared. That would leave dv to be e to the z dz. du would still be du dz times dz, but now that is 2z dz. So now du would be 2z dz. V, still the integral of dv, still the integral of e to the z dz, still e to the z. And what you get, if you do this, if you make this choice and apply the integration by parts formula, is u times v. So you get z squared, e to the z, minus the integral of v du. V is e to the z, and du is 2z dz. So times 2z dz. But you can pull out the 2, right? Anti-differentiating is linear. You can pull out the constant. And you've got minus 2 times, but then the integral you would have left to do is the integral of z dz, z e to the z dz. That's the one we integrated a minute ago by parts. So yes, you're getting somewhere. The power of z dropped, and we're now at the integral we had a minute ago. So you'd integrate by parts again, letting u be z and dv be e to the z dz as we did before. And yeah, you'll get an answer. So you keep letting u be the power of z until until all the powers of z go away and you just integrate e to the z dz. So I'm not going to finish this, but that's what you do. We're where we were when we started the other problem after you pull out the 2. And don't forget the minus sign. All right, but let me do 2 integrals by parts where you have a power, well, in the first one you clearly have a power of t. And then I want to do a similar one that bizarrely doesn't even have a product of functions in the integrand and is still an integration by parts. So let's look at the integral of t to the 5th times the natural log of t dt. Suppose we want to calculate this antiderivative. You see the product of 2 very different looking functions of t, and so you might suspect it's kind of related to the product rule, so integration by parts. You could try a substitution. I don't know what you would pick for u. Nothing would really work. So you want to, let's do this by parts, which means we want to write this as the integral of u dv. So there are 2 reasonable choices that you might make. You could let u be the t to the 5th part, and dv would be the leftover part, so ln of t dt. Or you might try u equals the ln of t part, and that would leave dv to be the t to the 5th dt. Well, again, one of these works and one of them doesn't. And this time, picking the power of t to be u is actually bad. And the easiest way to say why it's bad is because that means dv is ln of t dt. And so v is the integral of dv, so it's an antiderivative of the natural log of t with respect to t. You might think you know this, but you probably don't. And if you do, I don't know why you do at this point, because you know an antiderivative of 1 over t. That's the natural log of the absolute value of t. In other words, you know the derivative of ln of t. It's 1 over t. And a lot of people, when they're moving fast, just write, the integral of ln of t dt, 1 over t. No, that's its derivative. You don't know this. You don't know something whose derivative is natural log, presumably. But you always have to be able to integrate whatever you end up having for dv. So anytime you're integrating by parts, whatever you have for dv better be something you know how to antidifferentiate. And we don't know an antiderivative of ln of t. I do. You probably don't. So this is a bad choice. And this choice, kind of amazingly, will work out really well. And the reason it works out so well is because du will be 1 over t dt, and it'll wipe out part of what we get when we integrate this. So this will work. Let's do this. If u is ln of t, du is the derivative, that's 1 over t times dt. V is an antiderivative of dv, that's an antiderivative of t to the 5th dt. It's the power rule for integration. You add 1 to the exponent and divide by the new exponent. And as before, you don't bother putting in a plus c on the v. So integration by parts. So with this choice of u and this being dv, this integral is the integral of u dv, which would be u times v minus the integral of v du. U times v, ln of t times, so this is ln of t times t to the 6 over 6 minus what? V du. V, t to the 6 over 6 du, 1 over t dt. And you hope that this new integral is easier than the one you started with. Well, it is, because there's t to the 6th and then divided by t. That's t to the 5th. Well, you know how to integrate that. So what we get, this is very bad board organization. So what we get is t to the 6th times the natural log of t over 6 minus the integral. All right, I'm going to pull out the 1/6 in the denominator and t to the 6th divided by t to the 5th. So we get minus 1/6 the integral of t to the 5th dt. And now you use the power rule again. So you get t to the 6th times the natural log of t over 6 minus 1/6. An antiderivative of this, you add 1 to the exponent, divide by the new exponent, and add a plus c. So this is our answer. You could neaten this up a little bit by writing this as minus t to the 6 over 36, but this is what you get. All right, I'd like to do one last integration by parts problem, just as an example of how some things can be integration by parts that don't even have products in them. It's a little surprising. It's probably not something you would guess without having seen an example. But let's do the example of just the integral of natural log of t, the thing I said that you don't know, presumably. Why on earth would you suspect this is an integration by parts? You probably wouldn't. But if someone said, integrate it, well, there's no nice substitution to make. And at some point it might occur, and you don't know something whose derivative is ln of t. So if you're going to be able to anti-differentiate it, it kind of better be integration by parts because you only have so many techniques. But this would mean that we need to let u be, well, the only thing that it can be, well, it could be 1, but then dv would be this, and to find v would mean do this integral. But the other choice is let u be the whole ln of t. That leaves dt, or that leaves dv is just dt. Is this going to work? So yeah, if this is u and this is dv, then this is the integral of u dv. And that should be u times v minus the integral of v du. All right, what do we get? Well, du is the derivative of u with respect to t times dt. So it's 1 over t dt. If dv is dt, then v is always the integral of dv. That's the integral of dt. That's just t. Again, you don't put the plus c. So what's u times v? It's ln of t times t. So we get this is ln of t times t minus the integral of v, which is t, times du, which is 1 over t dt. But the t's cancel. And this is just the integral of 1 dt, which is just t. So rearranging this, just so we don't need all the parentheses, this is t times the natural log of t minus the integral of 1 dt. That's minus t plus a constant. And that's it. That's the antiderivative of ln of t. You can memorize that now if you really want to. It's not something that comes up terribly often. It is nice to know that it's known. Anyway. There are more anti-differentiation formulas. I didn't talk about, the derivative of inverse secant. If you read that formula as an anti-differentiation formula, all the derivative formulas yield anti-differentiation formulas. Seriously, only the quotient rule is completely unused as an anti-differentiation formula. It would be like a really, really, really awful integration by parts kind of thing, and it's just not done. All right, in the next section, we will we'll solve some differential equations that aren't just dy dx equals some function of x, but you have to know how to anti-differentiate before you can do those, so we needed to do this